Hello, friends. This is Jim with Science Talk. I thought I would do basically a part two of my introductory talk on linear regression. In the first video I did on this, I explained to you what the R square and R parameters are and what they measure. I talked with you about fitting a line through the data point or some sort of a curve through the data point, and I went through some examples with you. And it's just the whole idea of being able to use that as a predictor for whatever situation one is trying to model. What I thought I would do here is extend this a little further, and it kind of calls into review, I guess you could say, some of the concepts I presented in my very first video on statistics that I did, where I talked about hypothesis testing. So what I've done here is I've written out the general, and I'm keeping this really simple. I've written out the general linear model. Y hat, the predicted value, is equal to the b sub 0, which is the y-intercept, and that is represent an estimation, would be a better word, an estimation of the parameter beta sub 0, Greek letter beta, plus b1 times x. b1 is, of course, the coefficient, basically telling you the slope of the line. And b1 estimates the parameter beta sub 1. Now the question is, okay, you can come up with a regression model. And I wrote one out here for you right here. Okay. Y hat is equal to 4.31 plus 0.117 times x. Now the question becomes, okay, we have this value right there. We have the slope of the line. An important test is to see, is this slope of the line significant? In other words, is the independent variable, is it useful in helping to estimate the response? So we have a way of testing that. And the way we test that is we have a null hypothesis that b1 equals 0. In other words, we would have a flat horizontal line which would give us a constant function, y hat equals b sub 0. Right? So we're looking at this b1 equal 0. That's the null hypothesis. The alternate hypothesis would be that b sub 1 does not equal 0. Now note, we're not specifying that b sub 1 is going to be greater than 0 nor less than 0. We just simply want to know, will this coefficient, will this slope be non-zero? It could be positive, it could be negative. If it's negative, then we know the function decreases as x increases. Positive function increases as x increases. So this would be the alternate hypothesis. Because we have a does not equal, when we do the appropriate testing, we would have to use a two-tail test, basically checking on either side, greater than or less than. Note, if we had simply a greater than 0, it would be a right-hand test. Less than 0 would be a left-hand test. But we just want to simply know, does b1 not equal 0? So therefore, it's a two-tail test. So if you, and we have a way to calculate, and this is using a t-test. We have a way to specifically calculate this, and we would get a test value, and we compare it to the critical value, which would be based on the degrees of freedom, and we look it up in the t-tables, and we make a determination. Or, you might recall from that video, we can use probabilities. So let's say we ran this test at the 95% level. Well, a probability value that's less than 0.05 would yield a significant result. So if we got a probability value of p equals 0.003, that's less than less than 0.05, it's less than that, we would reject HO, accept HA, and basically say, yes, this is useful. the slope is not 0, this is useful to determine the response in the dependent variable. Now, if my p-value was greater than 0.05, we would accept HO, and therefore we would note that this is not useful. We basically have a flat line, a constant function, and there we have it. Now, if we were looking at the critical values, a critical value that is, the test value, if we're looking at a test value comparing it to the critical value, if the test value is greater than the critical value, we go with HA. If the test value is less than the critical value, we go with HO. So that's why oftentimes it's just, and most of the computer programs, they calculate a p-value. Pretty much you just look at the p-value, compare it to 0.5 or 0.1 if you're at the 99 level. And if it's less than that, reject HO, go with HA. So now let's say we have the result that, okay, we're going with HA, that this is useful, the slope is not 0. We can then calculate a confidence interval around the coefficient. I've discussed with you before in that very first stat video about confidence interval. And there's a way to directly calculate this. And now, granted, I'm just making these numbers up here, but it's to illustrate the concept. And basically, we can calculate a confidence interval around the coefficient. We may get something like this, 0.077 to 0.147. What does that mean? Let's say it's a 95% confidence interval. That means that 95% of the time, the true value of this coefficient is within this interval. That's basically what it means. If I calculate 99% confidence interval, then the true value of this coefficient would be 99 times out of 100 within whatever the interval that was calculated. So we can do that. And that's the general idea of confidence interval. You know, my students used to say, we're 95% confident. I like to say 95 times out of 100, the true value is within these calculated intervals. The best way of thinking of it. So when you look at a paper and they're reporting a regression line, you can look at what's the R-square. That tells you how well fit the data point is to the curve, the line, what have you. We can look at R, which tells you how the variables are correlated to each other, negatively or positively, strongly, weakly. 0 is none. If you have 0 for R, you're pretty much going to have a poor R-square. If you have a high R-square, 0.85 or greater, then you're going to have a pretty decent high value of R, positive or negative, but the variables will be correlated. So you can look at that, and then you can now also look at, okay, the coefficient, and sometimes the paper will give you the p-value telling you that we tested this hypothesis, and we found that HA is the situation, this is normal, and then sometimes they'll give you a confidence interval. Not always, but sometimes. Those are some of the things you can look for. Now, of course, you can, I started with a simple one here, but let's say I have B sub 2 and X sub 2. I can perform the exact same test for each of these coefficients. Sometimes you may even have what we call an interaction effect. I'll call it B sub 3. And you have X sub 1 times X sub 2, where the variables themselves, there's some sort of interaction between the independent variables themselves. And again, you could run a test on that to see if that is significant. So let's say you run a test on that and you find that this is significant. Then this becomes part of your model. That means there is an interaction between the independent variable that is helping to shape the response of the dependent variable. If this turned out to be this situation here, where we can reject that, then we, with basically that's equal to 0, then we can eliminate that from the model. And it may be simply, b1x, and I guess that since I put in b2x2, let's put in the b1x of 1 there. So it might be simply that, okay, this is the model we go with. And I illustrated that in my previous stat in linear regression video, where I talked about maybe you have an r squared 0.74 with just this, you add this in here, now you get an r squared 0.94. So obviously that situation. Now, if this were significant and you add in this factor here, then your r squared might bump up to 0.98. Then you got a really good model. But if this has a situation where this is, we can eliminate that term, then this is not going to affect the r squared all that much. So we develop the models, we come up with the parameters, we come up with the variables, we come up with the coefficients, and then we test them to see which is actually contributing to the response. So I'm not going to have this video as lengthy as the previous one on the Intro to Linear Regression, but I thought this was an important one as a follow-up to share another aspect of how to critically look at when regression models are presented in a paper. I said I'm presenting the basic situation. Of course, models can get more complicated, but the general principle still applies. So thank you for your time, and I hope you found this informative, and we'll talk soon. Hey folks, just a reminder to please subscribe and click the bell so you know when I drop a video. Please share my videos, please tell others of my channel and of the work that I do. I also hope that you will consider becoming a patron at patreon.com/Science Talk with Jim Massa, where from time to time I upload videos there exclusively for my patron subscribers. Details in the description box below. Thanks.